Good morning, chemists. Good morning. Good morning, chemists. Let's get started. So we'll continue on with chapter 3 today, but we're probably not going to finish chapter 3, so that means there will be no homework set due this weekend, so yay, little wins, but I do encourage you to get started on that homework set because it is fairly long. It's like 2 hours, maybe even more, because there's a lot of very important concepts that come from this chapter. All right, so this will be the last time I announce this about this GE interview thing that many of you have been assigned. It's due, I think, next week. If you have no idea what I'm talking about, then just ignore what I'm saying. But I'm going to do one large interview this afternoon at 4:10 in a McPherson classroom. But to get that information, it is a page in our lecture resources module. It's at the very, very top. So if you have any questions about that interview this afternoon, just go to this page. You see the room, the time. I have a shared document that we'll work through and answer questions together, so we can basically share notes. And then there's also a Zoom meeting if you want to attend virtually. If you can't make it at 4 p.m., then I will be posting the recording on this page as well for your convenience. All right. So that's the last time I will mention that. That will happen tonight. Okay, so let's continue on with chapter 3. We stopped at a really great point on Tuesday where we introduced a new conversion factor, a new derived unit, grams per mole or molar mass. And we see that within that unit, molar mass, grams per mole, allows us to convert from the gram amount of stuff that we weigh in lab and relate it to the mole amount of material that is there. So we did some practice using molar mass as a conversion factor. We also used Avogadro's number. I do hope that you memorize this. I need to double check and see if you were given that value on exams. I'll figure that out. And then finally, if we can relate a mole amount to number of particles, we can also determine how many elements or atoms of a certain kind are present in a sample, as long as we know what that chemical formula is. If we have 1 mole of caffeine particles, then we have 8 moles of carbon atoms there, because there are 8 carbon atoms in every one formula unit. All right, so yeah, we introduced that, we can weigh a single carbon atom, the value off of the periodic table, 12.01 AMU, so atomic mass unit. That's the mass of just one tiny carbon atom, but you'll never work with just a single atom in lab. So instead, we talk about mole amounts of stuff. And moving forward, we will almost exclusively talk about mole amounts of stuff. The numbers off of the periodic table are still good to us, but the unit just changes. It's grams per mole now. So we'll be using that extensively in this chapter and basically the rest of your chemistry career. All right, so I need to introduce the concept of percent composition of substances based upon their chemical formula, because this will lead us to the next learning objective, and that is calculating empirical formulas from percent composition data. So we'll finally take out of our back pockets from chapter 2, what is the significance of an empirical formula, the simplest ratio of atoms present. So percent composition is exactly what it sounds like. If we know the mass of our entire substance, we can break down the masses of that substance by its elemental composition. So here's an example, CH4. There's a carbon atom and 4 hydrogen atoms per every unit of that molecule. So you can take the atomic masses or molar masses off of the periodic table, and you can get an entire molar mass of a CH4, a methane unit. So that's right here, all right? So that's the molecular weight, or you can say molar mass of a whole CH4 molecule, right? You could do that work yourself in calculating that, yes, CH4 weighs 14.04 AMU or 16.04 AMU or 16.04 grams per mole. That 2 subscript, I'm just keeping some sig figs. I'm trying to tell you, hey, that 2 is not part of the sig figs value that I will report, but I want to keep them in my entire calculation. All right, that's the mass of the whole thing. So we can calculate how much of that sample is carbon, how much of that sample is hydrogen by just massing up each of those elements individually. So I've done that work for, whoops, I'm sorry. Slippery hands. I've done that work for you where, okay, we see that there's one carbon atom. So let's take the weight of that one carbon atom, so 12.01, divide it by the whole. So I'm doing the part over the whole and multiplying by 100 to say, oh, this sample is about 74% carbon by mass, all right? So nearly 3/4 of the mass of methane comes from the carbon atoms versus hydrogen. Notice that there's 4 hydrogens here because of that chemical formula. So do make sure you account for all 4 of those hydrogen atoms. So I'm going to just do 4 times the mass of 1 hydrogen. And again, divide it by the whole, multiply by 100 to get, okay, 25% of that sample is hydrogen atoms by mass. So it's 25% hydrogen by mass. And so we've accounted for all of the atoms in this molecular formula. There's only carbons and hydrogens. So if we take those 2 numbers, we can check our work by adding them up, and we should see, yes, this adds up to 100%. All right, so 3/4 of the mass of methane is carbon, 25 or 1/4 of the mass is hydrogen, and of course that adds up to 100%. If you did this and you didn't get 100%, then something probably went wrong. Either you forgot, to account that there's 4 hydrogens, would be a common mistake. So I did all of this in AMU, but you could also do it in molar mass. It's the same numbers. You're just working with different amounts. I just looked at 1 CH4 molecule, or you could talk about a mole's worth of methane CH4. All right, so we'll talk about why this is significant in a tiny bit. All right, so let's practice this. Rust is iron 3 oxide. If you have the old notes, I accidentally put the formula there because I want us to, practice chapter 2 material in that if I give you the chemical name, so in this case, iron 3 oxide, we should be able to conjure up what that chemical formula is, because the chemical formula is super important for percent composition because we need to know how many of each element is present. So our guiding questions here for this overall question is, what is the mass percent of just the iron in iron 3 oxide? Our first part of the strategy is let's get that empirical formula of iron 3 oxide. So this is basically a chapter 2 question. Based upon this name, what is the full chemical formula? We can't just simply say FeO. We can't just say, oh, it's 1 iron, 1 oxygen. We have to inspect the charges because this is an ionic compound. So if it's ionic, we can usually tell what the charges are based upon the name. Iron 3 has what charge? 3+, yes. We don't memorize that because iron is a variable charge cation. The name, iron 3, is telling you, hey, this is iron 3+. But oxide is something you did have to memorize. Oxygen as an ion is always what charge? 2-. There we go. Now we swap those superscripts to make them subscripts to make it charge balanced. So we should see that iron 3 oxide has the chemical formula Fe2O3. All right, so those, again, subscripts, super important for the next step because we need to determine what is the entire mass of this thing. All right, what is the entire mass? And then we need to figure out how much of that sample is iron. All right, so we'll be using our periodic table here. To do this calculation, we need the mass of just the iron in the sample, and then we need the mass of the entire substance, Fe2O3. So I should say mass of all of the iron because notice that there are 2 iron atoms for every formula unit. All right, so here is our chemical formula. So I'm going to calculate that entire molar mass of iron 2 oxide. So I will take inventory. I notice that there are 2 irons. There are 3 oxygens. And so 2 times what is iron? 55.85. I'll work in grams per mole. You can do AMU as well. It doesn't really matter. And then there are 3 oxygens, so that is 16.00. All right, and we'll add those 2 things up. Remember, this is addition sig fig rules because we're just adding all of these numbers up So the number of sig figs for our final answer should go out to 2 decimal places, however many that is. So even though both numbers have technically 4 sig figs each, this is addition, so we need to look at place values, so 2 decimal places for each. All right, so if you put that in your calculator, you see 159.70 grams per mole is the mass of the entire iron oxide formula. So that will be our denominator in our percent iron calculation. All right, so we got that number on the bottom. Is that 159 number we just got? Now we just need the mass of all of the iron. So we already kind of have that calculation right here. We just need to figure out how much of this total mass is iron. So it's just going to be 2 times that 55.85, and that is equal to, let's do a different color, 111.70 grams per mole is the mass of just the iron atoms. So those are the 2 values that I'm going to divide by. All right, so let's do that. 111 divided by 159.70. We'll multiply that by 100. So at this point, it is multiplication division, so we do want to look at number of sig figs. So again, because of the addition rules, all of these numbers go out to 2 decimal places, but each of those numbers have what, 5 sig figs? So our percent composition here should have 5 sig figs because this last operation is multiplication, right? So 69.94% iron, right? If we wanted to calculate the percent composition of oxygen in this molecule, the easy way to do that would be to just subtract this number from 100, right? Because the rest of the sample has to be oxygen. There's only 2 elements present. Or you could also use our same strategy here and just determine, okay, how much of this mass, 3 times 16, is within the full mass of the compound. So what is that? 48 divided by 159 should be the same number if you subtract that from 100, all right? All right, so those are percent compositions. We're just looking at the masses of each of those elements present, making sure you take note of those subscripts and dividing it by the full mass of that compound to determine how much of the mass contributes to the full molar mass per each element. All right, so why is that important? Why do we need to talk about percent composition? Because this is a way that chemists back in the day were able to determine the chemical formula of mystery substances, all right? You know, I can't just look at a sample and know its chemical formula. I have to do some experiments in order to determine that. Like I don't have a special, instrument in lab that I can just stick it in and it spits out a chemical formula. So how chemists were able to figure out the chemical formula of mystery substances was by determining the percent composition of those substances. Like you could do combustion analysis or other types of instrumentation to determine, you put your sample in and you go, oh, it's, 50% carbon atoms, or 50% by mass carbon, it's 25% by mass hydrogen, and 25% by mass oxygen, for example. And so from that data, from percent composition data, we can actually get an empirical formula. And so these are the 5 steps to determine an empirical formula from percent composition data. If you master these 5 steps, you will be right every single time. Right, so I'll just quickly go through these steps, and I think it's better if we just do some examples here. All right, so if we give you percent composition data, these are the 5 steps to arrive at an empirical formula. So first, we'll give you percentages, all right? So the first thing you want to do is express the composition of those elements in grams first. So if I tell you that your sample is 61% carbon, 39% hydrogen by mass, how we can convert this into masses is just assume you have 100 grams of sample. If you have 100 grams of sample and you have these percent compositions by mass, how much carbon is there? 61 grams of carbon, yes. And then for hydrogen, you have 39 grams of hydrogen, all right? So that's how you convert those percentages into masses. Just assume you have 100 grams of junk, so those percentages become grams, gram amounts. So what's great is now that we have gram amounts of each of the elements. So from that information, we can turn the gram amounts to mole amounts of each element using molar mass that we just learned about last lecture, right? That's why we needed to convert it to gram amounts, all right? So convert those gram amounts to mole amounts. All right, then after that step, after step 2, you're gonna have mole amounts that look really ugly. There are gonna be tons of decimal places. So this is really important. Step 3 is identify the smallest mole amount you have and divide all of those numbers, all of those mole amounts that you calculated in step 2 by that smallest number. Doing this ensures that one element has an integer value present. And I'll show you what I mean there. It's how we get the ratio into whole numbers. All right, and so once you divide that smallest mole amount, hopefully you'll have whole numbers, and then that will give you your ratio. But if they're not whole numbers, we have to kind of do some finagling to force them to be whole numbers. So for example, actually let's just do an example, and then we'll come back to this 4th step. All right, okay, so here's the strategy. I give you percentages by mass of each element. This is your strategy. Turn those percentages into grams. Turn those grams to moles. Then identify your smallest mole amount, get your mole ratio, and then you should be pretty close to your empirical formula. So let's look at this information given. We have 68% carbon, 8% hydrogen, and like 22% oxygen. So what I like to do, these are going to be 3 different calculations. So what I'm going to do is do this first step, convert all of those percentages into gram amounts. So again, we're going to assume we have 100 grams of sample. So if 68% of it is carbon, then that means I have 68.54 grams of carbon present in this 100 gram sample. Then we will have 8.63 grams of hydrogen, and then 22.83 grams of oxygen. Right, so we did that first step. The next step, we want to use the molar masses of the respective elements and convert those gram amounts into mole amounts, but for each of those respective elements. So pull out your periodic table or look up here and notice for carbon, carbon has a molar mass of 12.01 grams per mole. So if we convert that into an equality, what that means is that there is 12.01 grams of carbon in 1 mole of carbon, all right? So if that's what the equality means, where am I going to put the 12, on the top or the bottom? On the bottom, yes, because right now I'm in grams, and I want to cancel that out, so 12.01 grams of carbon goes on the bottom, 1 mole of carbon goes up top. For hydrogen, we're not going to use 12. We'll use the molar mass for hydrogen, which is 1.008. Again, gram is going to go on the bottom. 1 mole is going to go up top. And then hydrogen is last. If you look at the periodic table, it is 16 grams per mole. So 16.00 grams of oxygen is in 1 mole of oxygen. So I do it all together. I do all the work, and then I plug it all into my calculator. So I'm going to convert all those gram amounts to mole amounts. So I see that there is 5.707 moles of carbon present in this 100 gram sample. There's 8.561 moles of hydrogen. And then there is 1.427 moles of oxygen. All right, cool. So now I have mole amounts. But we're not done here. This is not an empirical formula because, you know, in chapter 2, did you ever see chemical formulas with fractions in them? No, all right? We can't write, oh, carbon 5.7, hydrogen 8.5, oxygen 1.4. That's not a chemical formula we've seen. So we need to force these numbers to be whole numbers. But what we're not going to do is just round them. Don't round this to 6. Don't round this to 9. Don't round this to 1. Instead, what we're going to do is identify the smallest number that we just calculated, and that happens to be the mole amount of oxygen, right? So that one's the smallest. So we're going to divide all of these numbers by 1.427. 427. By doing this, we ensure one of the mole ratios is an integer value, because what is a number divided by itself? It is always 1. So by doing this, we force 1 mole of oxygen to be present, right? So then the rest of the stuff, what you'll see is other numbers come out. So we forced oxygen to be 1. If you do the hydrogen calculation here, you get 6.002 moles of hydrogen, and then carbon is something like 3.99 moles of carbon. All right, we're getting a lot closer to an empirical formula. So 3.99 is basically what number? 4. Yeah, so this rounds to 4. So there are 3 moles of carbon present. 6.002 is very, very close to 6. All right, what mole of hydrogen? And there it is. There is our mole ratio that gives us our empirical formula. So this compound has this formula, C4H6O, one of them, right? So notice here that when we did the division of the smallest mole amount, we got numbers, yes, that had, decimal places in it, but they were very, very, very close to a whole number, 3.999 or 6.002. Those are fine to round because they're really, really close to an integer. All right, so here, let's go back to step 4 here. All right, because sometimes you won't get an integer value, and I'll show you what you do in the next example. So here's an example. If you got a mole amount of 1.96, this basically rounds to 2. All right, because it's very, very close to an integer value. But what about if you did all of that work and you got a mole amount of 2.501? Does this round up to 3? Technically it does, right, if we were like doing sig figs, but in this case where we're trying to find the simplest ratio of atoms, we're actually not going to round this number. We don't want to round it up to 3. Instead, we're going to multiply all of the values, all of those mole amounts by 2. Because if you multiply 2.501 by 2, you get a number very, very close to 5. And that is a whole number, right? Or what if you put, do all that work and you get 2.33? Are we going to round that down? No. What are you going to do? You're going to multiply all of your mole amounts by 3 because 2.33 is equal to, what is it, 7? Yeah. So you'll get something like 6.99. That is very close to 7 moles, all right? What if you had a number like 1.66? Do you round that up to 2? Nope. What are you going to multiply by? If you don't know, just guess and check. Okay, you're going to multiply by some type of integer value. So 1.66 times what number gives us a whole number? 3. Yeah, by 3. And so 1.66 times 3, what is it? Is it 5? Yeah, it's 5. Okay, so it's 5. All right. So let's do an example that actually doesn't have a whole number, and we'll have to do that. All right. So don't round. Okay, don't round if the number is not very, very close to an integer value. All right, so here's another problem. So we have a compound and it's analyzed to contain 4 grams of phosphorus, 5 grams of oxygen. Determine the empirical formula. So remember, the first step with empirical formula calculations is to get those elements into gram amounts. Typically, we give you percent compositions, and I tell you, oh, assume you have 100 grams of sample. But in this case, I already gave you the gram amounts of everything. So we actually just skipped this first step. Oh, wait, no, we didn't. Not that first step. We skipped the percentage part, and we're actually just going to start with the gram amounts. So there's no reason to convert percentages into grams because we already have gram amounts here. So I'm just going to go ahead and use them. So there is 4.37 grams of phosphorus present and 5.63 grams of oxygen, right? Because the whole point of getting it into gram amounts is so then we can use molar mass to convert it into mole amounts. So we'll use the periodic table. What is phosphorus? 30.97. So 30.97 grams of phosphorus is 1 mole of phosphorus, and oxygen is 16.00. 1 mole of oxygen. Right? So this sample has 0.1411 moles of phosphorus present and 0.3518 moles of oxygen. This math, sig figs don't really matter because we're going to end up just trying to get a whole number. So just give yourself enough decimal places here. 3 or 4 is probably sufficient to figure out what that whole number ratio is. All right, is this my chemical formula? No, it's not. So we need to force them to be whole numbers. So we're going to divide by which number? The smallest one. So we're going to divide by this one. So 0.1411. This forces there to be 1 mole of phosphorus present. But then if we divide the mole amount of oxygen by this 0.1411 number, we get, what is it? 2.493 moles of oxygen. So what is this chemical formula? Is it going to be PO2? Are we going to round that down? We're not going to round it at all. What we're going to do is recognize that this 2.49 number is really, really close to 2.5, right? And so what we're going to do is multiply all of these numbers that we just got. We're going to multiply by 2. Right? So then if you multiply by 2, the new oxygen mole amount is 5 moles of oxygen. But since we multiplied the oxygen one, we also have to multiply the phosphorus one. So there's going to be 2 moles of phosphorus and 5 moles of oxygen in this sample. All right? So be very, very careful when you're doing this empirical formula calculations and divide by the smallest one that, you know, we only round to the integer when it's really close. But sometimes you'll see fractions where it's very clear, oh, you need to multiply by some type of value here. So in this case, 2 to get rid of that fraction. Yes, question? So in an ionic compound, no, like if NaCl, right, that's a 1-to-1 ratio. That is exact. That's exact. We'll see the effects of different ion ratios in chapter 4. So for example, NaCl has 1 cation, 1 anion, but an ionic compound like calcium chloride has 1 anion, 1 cation, 2 anions. So there's a total of 3 particles there. So both of those substances would have different empirical formula calculations. We will also see different properties of those substances because one of them has more ions present. It's related to conductivity. There's just one example. All right. Okay. All right. So, all right. So how do we feel about those? Okay. So if you memorize these 5 steps, practice them, you will always be right. All right. Okay. Okay. So notice that we were always calculating empirical formulas. Like our classmate said, ionic compounds, like we could do this for an ionic compound, we would get the empirical formula. So like NaCl, that's the empirical formula. But there are compounds out there where the molecular formula is different from the empirical formula, all right? So when scientists did this percent composition experiments, they could only, from percent composition data, get and calculate the empirical formula. In order to calculate the molecular formula of the full molecule, we actually have to introduce another experiment. So let's just reintroduce the idea of empirical formulas from chapter 2, because now it's important. Now we care about it again. So I think we looked at this chart before. Empirical formula means simplest ratio, all right? So when we look at these subscripts, typically we can identify what is the multiplier that is related to the subscripts that are here. So for hydrazine, the multiplier is 2, and the empirical formula is NH2. Do you agree with me? Yes. So why what we just learned is important is because all of that percent composition data can only help us calculate empirical formula. Okay, percent composition. That's all we can calculate. So for example, if a chemist determined the percent composition of hydrazine, all they could calculate is the empirical formula. They couldn't get the molecular formula without another piece of information. So let's do the rest of these. Benzene, what is its empirical formula? CH, and its multiplier is 6. Acetylene is also CH, interesting, and its multiplier is 2. And then water, its empirical formula is the same, it just has a multiplier of 1. So here's the idea. If you do the percent composition data for an empirical formula analysis for benzene and acetylene, you'll get the same empirical formula. You won't be able to distinguish if your sample is acetylene or is it benzene simply by percent composition data, because they both give you the same empirical formula. So this slide, the takeaway here is how to go from an empirical formula to a molecular formula is you need the molar mass of the whole compound. That is how we are able to go from empirical formula to molecular formula, all right? So everything we just did, the 5 steps that we just did, can only have us calculate empirical formulas, the simplest ratio. So if you have a more complex molecule and you want to figure out its full formula, you also need its full molar mass, all right? Because if you know how much it weighs, the whole molecule weighs, and if you know the empirical formula, you can figure out, oh, how many empirical formula units have to go into that full molecule. You can figure out what the multiplier is, all right? So let's do an example, I think. Yes, okay, so here, I already did the empirical formula calculation for you. So if I tell you, like, let's say we did the 5 steps, and we determined that a molecule had an empirical formula of CH2. That's not the full molecule, all right? So I want to determine what is the full molecular formula, so the additional piece of information I need is its full molar mass. And I tell you that this molecule weighs 70 grams per mole. What is the full molecular formula? So if we know about empirical formulas and we understand it, we understand that that empirical formula is the simplest ratio. So the molecular formula has to be some multiple of that, right? We know that the molecular formula has to be like CH2 or C2H4 or C3H6. We just need to figure out which one. So what I'm going to do, all right, I know that the empirical formula is CH2. I want to know what is the molecular formula, okay? I tell you that the mass of the whole molecule is 70 grams per mole. So if we figure out how much does 1 unit of this empirical formula weigh, I can figure out how many of those units are within the full molecule. So carbon, and we can just estimate here because we're trying to get just a whole number. So carbon weighs about 12 grams per mole. 2 hydrogens weigh 2 each, so 2 times 1. So if you add that up, this empirical formula weighs about 14 grams per mole. Do you agree? About 14. We don't have to be super exact here because we just need to figure out what is that multiplier. That multiplier is going to be a whole number, all right? So you can just guess and check and figure out, okay, how many times does 14 go into 70? Or you can just use your calculator and do 70 divided by 14, and what do you get? 5? 5. All right? So 5 of the empirical formulas go into the molecular formula. So once you get that 5, you're going to do the same thing to that entire formula. So that means this molecule has a molecular formula of C5H10, right? And that kind of highlights, in order to fully know about the molecules that chemists back then were studying, they needed to know both the percent composition and its full molar mass in order to determine its molecular formula, all right? So that's the takeaway there, that percent composition data only tells us the simplest ratio, the empirical formula. And so in order to get the full molecular, we also need that molar mass. And that is why we learned about empirical formulas in chapter 2, because a lot of folks were like, why would I ever want to, report this molecule in an empirical formula? It's because this is what came from data. So remember, empirical means by experiment, by observation, and this is exactly what chemists did. All right, so let's finish up this section to see if you have taken away not just, the 5 steps in the strategy, but the big picture. What is the significance of empirical formula, molecular formula, and how that multiplier is important. So let's consider benzene and acetylene again, all right? So here's benzene, C6H6, and here is acetylene, C2H2. But pretend that, you were a chemist way back when and you didn't know like what these compounds were. They were just mystery substances to you. So tell me these statements, true or false. Benzene and acetylene have the same molecular formula, true or false? False, right. So we are comparing C6H6, C2H2, they're absolutely different. But benzene and acetylene have the same empirical formula. They do, yes, they're both CH2. So benzene and acetylene have the same percent carbon and hydrogen composition. That is true as well. You can try it yourself. You can calculate how much of your sample is carbon in benzene. Oh, it's not CH there. Okay, all right, is that better? Yes. Sorry, it's just CH. If you calculate the percent mass of each of those elements in each of these compounds, you'll get the same exact number. And the reason is because they both have the exact same empirical formula. All right, so yeah, that's true. Benzene and acetylene can be identified by just a percent composition data analysis, true or false? That is, false, yes, false. Because what does percent composition data tell us? Just the empirical formula. And because both of them have the exact same empirical formula, we can't tell them apart. All right, acetylene and benzene have the same molar mass, true or false? Super false, yes. They have different formulas, so they'll have different weights, all right? And then the last one, benzene and acetylene can be identified if percent composition is known and the molar mass is known. That is true, all right. So if we work through these true and falses and got it fairly quickly, then I think you've gotten the point of empirical formulas and relating it to molecular formulas and molar masses. All right, so this was definitely application of using molar masses that we introduced in the last chapter, but we're using molar masses to understand more about the compounds around us. So I want to do a demo here and celebrate us moving on to the next section, which is stoichiometry. All right, so we're going to learn about stoichiometry in this last section, and this is kind of like the meat and potatoes of chemistry. Like if you've taken chemistry before, stoichiometry, I don't know, sometimes has a bad connotation. Some people think it's fun. I will teach it a very specific way, building off of the dimensional analysis I introduced back in chapter 1. So let's celebrate us starting stoichiometry and really getting into the chemistry by blowing something up. All right, so I did this demo in my review session, but I want you guys to see it too. It's not loud, but it's fiery, all right? So this is the rapid oxidation of sucrose that we're gonna do. It's the screaming gummy bear demo. And then I have a picture here. I just got my ducklings this morning. Yeah, so these are my 3 ducklings that I just taught them how to drink and eat this morning, and I'm so proud of them. I already named them. So I was at the post office at like 7 a.m. to get them. That's BG, Daisy, and Beaker. Yes. All right, so rapid oxidation of sucrose. Great. So celebrate us doing stoichiometry, celebrate my ducks, all of that stuff. All right. I was going to have us balance this equation, but I don't feel like it. It's kind of a hard equation to balance, so we're not going to do it. All right. This isn't loud, but it is fiery. And at my review session, I only put in 1 gummy bear, but they gave me 2. So should I put in both? Yes. Okay. All right. So you tell me. We've done a lot of demos here and explosions. I'm going to keep my promise of doing a demo a day. A demo every lecture, and if I don't have a demo to do, I'll just blow something up. Sound good? Okay, all right. All right, so let's see this one. Let's see if I can get both of these gummy bears in. Oh, no. Okay, it's not loud, but it's fiery. It's fiery. The products, what are the products? It's just CO2 and water, so we should be fine. We'll be fine. All right. Yeah, this demo had no point to it. It was just a celebration of making it halfway through the chapter. Is that all right? Okay. All right, yes. All right. So I'll just leave that fan on for a little bit for us. But yes, it's just CO2 and water. Yeah. Okay. All right. So, all right, let's move on to stoichiometry. Sorry, folks. Yeah, that is the one bad thing about this demo. Here, how about I? Okay, there we go. Is that better? I don't know. Okay. Okay. So in this part of the chapter, we're going to collect all of, really put molar masses and using molar masses to good use here. And we're going to be using molar masses to look at different reactions and look and see how do different reactions combine with one another, but relate it to gram amounts that we can actually measure in lab. So the big idea, you know, we did balanced chemical reactions back earlier in the chapter. And so the significance of those coefficients that we, you know, so carefully deduced is that those coefficients tell us how reactants combine, how much of each product is produced, but in different ways. So here in the, you know, combustion of hydrogen, so the hydrogen balloon demo, if we balance this, we see, oh, you need 2 hydrogen molecules to react with 1 oxygen molecule to give you 2 water molecules. So the 2, 1, and 2, I think it smells like marshmallows. The 2, 1, and 2, you can talk about it in terms of molecules, like, okay, 2 hydrogens molecules, 1 oxygen molecule, 2 water molecules, or more easily and more useful is we can consider it in mole amounts. So instead of saying, oh, 2 molecules of hydrogen combine, we can say, oh, 2 moles of hydrogen combine, 1 mole of oxygen combines to give us 2 moles of water. And that's super useful to us. And what we'll learn here is that these coefficients also are conversion factors that we can use in dimensional analysis. There's a picture of a bus here, because I always say the coefficients of a balanced chemical reaction are the ticket to get to ride the bus of the chemical reaction, right? Once we're in the unit of moles, all right? Actually, I misspoke. Moles is the ticket to get on our balanced chemical reaction, because we can look at these coefficients and say, oh, 2 moles of hydrogen equal 1 mole of oxygen. Or we can make the relationship different. We can say, oh, 2 moles of hydrogen instead, we can relate it to water instead. This is also equal to 2 moles of water. And you know I love equalities, because once you set something equal to one another, you can turn it into a fraction where one is on top and one is on bottom, depending on what unit you want to go to. So the basics of stoichiometry allows us to convert from one substance to another in a balanced chemical equation, but we do need some starting materials here. We need that balanced equation because we need those correct coefficients, and we also need to be in the unit of moles, right? So solving stoichiometry questions is really just dimensional analysis, where the balanced chemical equation gives you the mole-to-mole ratio of the substance you want to get to. So the basics of solving any stoichiometry question is you need to work in moles. But when we present questions to you, they are not given to you in moles usually right off the bat. So it's up to you to convert to moles first. All right, and then convert to the desired quantity you want. So here's an example. We'll just do a straightforward stoichiometry question. So how many moles of hydrogen would be formed by the complete reaction of 8 moles of potassium with excess water, meaning there's plenty of water present, so that's never going to limit us. So my strategy here is identify what are we given and where do we want to go to. All right, we're given how much potassium we have, but we want to go to hydrogen, right? So we need to ride the bus from potassium to hydrogen, but we have to be in the unit of moles in order to ride the bus, to go from reactants to products, to go from any substance to any substance on that chemical reaction. So looking at the information given, are we in the unit of moles already? We are. I tell you how many moles of potassium are here. So we already have our ticket to get on the bus. So looking at this balanced chemical equation, we get our mole ratio that we need. 2 moles of potassium is equal to 1 mole of hydrogen. So I'll write that out. 2 moles of potassium equals 1 mole of hydrogen. That's what the balanced chemical equation says. So if we start with what's given, 8 moles of potassium, now it's just like dimensional analysis. We're in the unit of moles of potassium. So I'm going to put the 2 moles of potassium, boop, on the bottom, because I want that mole amount to cancel. So notice that, yes, it's moles on this side and moles on that side, and I'm starting in the unit of moles, but we want to be specific to the mole amount of what substance. So I'm going to put 2 moles of potassium on the bottom, 1 mole of hydrogen up top, right? Not just canceling the moles, but the specific substance. So we see, oh, moles of K cancel, moles of K cancel. So we get, oh, we make 4.0 moles of hydrogen because that's the unit that's left on top, right? So I'm being super specific with my unit and the identity of that thing. So in this case, 2 moles of potassium, 1 mole of hydrogen, right? Let's take a note of sig figs real quick. All right, I give you a number with 2 sig figs, 8.0. These 2 numbers, the coefficients here, they look like they have how many sig figs? They look like how many? 1. They look like they have 1, but do they have 1? Nope, they have infinite. Yes, so that means we can just ignore them, all right? That these both have infinite sig figs because they're counting numbers, they're coefficients, right? We can count. There are 2 hydrogen molecules, 1 oxygen molecule. There are counting numbers, all right? So let's do another one that's a little bit trickier because it's not just 1 conversion factor. Same reaction, but look at how it's worded differently this time. This time, I still want hydrogen, but this time, I want you to tell me the mass of hydrogen that's produced. In the previous one, I just asked you the mole amount. So once we use that mole ratio, we were done. But this time, I want the mass of hydrogen. And I give you, this reaction starts with 15 grams of potassium. So I didn't give you mole amounts, and I want to get to gram amounts. But thankfully, we have a way to convert from mole amounts to gram amounts, and that is molar masses. So we still want to go from potassium to hydrogen. We're still going to use the idea that 2 moles of K equals 1 mole of H2, all right? But remember, in order to use this stoichiometry, this 2-to-1 ratio, we have to be in the unit of moles. So if we start with 15.5 grams of potassium, we don't have the ticket to get on the bus yet. We need to convert that grams to moles first. So how do we do that? Molar mass, yes, that we learned about earlier in this chapter. So our strategy here is convert that gram amount of K to mole amount of K using molar mass. So I already gave you the molar mass of K, it's right here. So 39.098 grams per mole. So that 39 goes on the bottom. So 39.098 grams of K is 1 mole of K. So now that we're in moles of potassium, it's just like the previous question now, all right? We're in the unit of moles. So now we can ride our balanced chemical equation to wherever we want. In this case, in this question, we want to go to moles of hydrogen. So now we can use our stoichiometry, all right? I like to think of this equality that I wrote, where I started and where I want to go. This is stoichiometry, going from mole amount of one thing to molar amount of something else using that balanced chemical equation. So I'm going to put the 2 mole of K on the bottom, 1 mole of hydrogen up top. So this was stoichiometry. This first step, this was the molar mass of potassium. Now the last step, because we're not done, if we finished right now and put it in our calculator, what would our unit be? moles of hydrogen. Is that what the question wants? Nope. Give it what the question wants. So the question wants grams of hydrogen. We're in moles right now, so we're simply going to use the molar mass of hydrogen. Yeah, molar mass of hydrogen. And I give you that too. It's right here. All right. But this time, where am I going to put the 2.016? Is it going to go on the top or the bottom? Top, yes. So 1 mole of H2 goes on bottom. 2.016 grams of H2 goes up top. And then the answer is down here. All right, 0.387 grams of hydrogen is produced. So notice here, the last step we did is we used the molar mass of hydrogen. So if I give you a gram amount and the question wants a gram amount of something else after a chemical reaction, you're going to be doing this a lot. Molar mass, stoichiometry, molar mass. Because stoichiometry relies on the idea that you have to be in the unit of moles. So we use molar masses to achieve that. So molar mass, stoichiometry, molar mass. You'll be doing that a lot in this chapter. So let's do a more fun one because that one was pretty boring. All right, let's look at this one. SpaceX's Dragon spacecraft uses a reaction between this thing and dinitrogen tetroxide in its thrusters. Here's the chemical reaction. All right, so this compound is the dinitrogen tetroxide, and then this one is the monomethyl hydrazine. What mass in kilograms of dinitrogen tetroxide is required to be stored in the fuel tank to fully react with 400 kilograms of the monomethyl hydrazine? So I'm telling you, oh, you have 4,000 kilograms of this thing. But I want to know how much of this stuff needs to react with it. So in the previous examples, we used stoichiometry to go from a reactant to a product. But the great thing about stoichiometry is you don't have to go reactant to product. Once you have all those coefficients, you can take the bus to go anywhere. You can get off the bus at any time. So in this case, we are going to get on the bus on the what's given monomethyl hydrazine and then get off on the other reactant, the dinitrogen tetroxide. All right, but it's the same strategy where we're going to use the molar mass of the thing given. We'll use stoichiometry. We'll use the molar mass of the thing we want. So let's collect those qualities here. So I can see from the balanced chemical equation that you need 4 moles of this hydrazine stuff, CH6N2, is equal to 5 moles of N2O4. Right? I give you that we start with 400 kilograms of the CH6N2 stuff. All right? We're in kilograms right now, so we're going to use our same strategy as before. Molar mass, stoichiometry, molar mass. Molar mass is in grams per mole. Right now we're in kilograms, so I'm simply going to convert this into grams first. All right, CH6N2. So I'm in grams. I want to go to moles of this stuff. So which number should I use, the 46 or the 92? The 46, yeah. So make sure that your molar mass matches with the thing you're trying to convert. So in this case, we're going to use the first one. We're going to use the 46. So 46.07 grams of that stuff is 1 mole of the hydrazine stuff. All right, so now we're in moles. So now we can get on the bus and use that equality we just wrote, using the coefficients. So I'm going to put the 4, where? On the bottom or top? Bottom, yes, because that is the unit that matches the unit that we're in right now. So this is 4 moles of CH6N2, and now we have 5 moles of N2O4 up top. If you've drank my Kool-Aid about dimensional analysis, you'll just see, oh, this is just like chapter 1, all right? It's just like chapter 1. It's just where we're getting equalities come from different places. In this case, an equality comes from the chemical reaction itself. All right, are we done? Nope, we need to go to a mass. So we're in moles, so let's get to a mass of this N2O4. So 1 mole of N2O4 weighs 92.01 grams. Are we done? Nope, got to go to kilograms. So we just need to divide by 1,000. 1,000 grams, 1 kilogram. Now we're done, right? So if you look closely past those kilogram conversions, notice we did molar mass, stoichiometry, molar mass again. You need to get very good at this, all right? Where we give you one thing, we want you to go somewhere else, get the molar masses of those two things, molar mass of the thing given, stoichiometry, molar mass of the thing you want. And that's how you go from gram amounts of one thing to gram amounts of another. And it all in the middle is that stoichiometry that must be in the unit of moles, right? All of those coefficients mean 4 moles of this react with 5 moles of this to give us 12 moles of water, 4 CO2s and 9 nitrogens. And we can't, it's all in the unit of moles. We can't use like gram amounts or anything. It's all moles. And so this is about a rocket ship. So just look at the products. The products are all what phase? Gases, all right? So wouldn't you want that in like a rocket thruster to make a butt ton of gas? Yeah, so that's why they use this substance to, this reaction specifically as a solid state, or I guess a condensed phase thruster. And so our answer is about 1,000 kilograms of the dinitrin tetroxide is what is needed. All right, so that was a cooler example, I guess. All right, so we got 25 more minutes, cool. So you need to get very good at molar mass, stoichiometry, molar mass, because we're going to use that skill in the context of more realistic reactions. So I have to introduce the idea of limiting reactants, all right? If you noticed in the earlier questions, these ones with potassium, where I asked you to go from potassium to hydrogen, right? We rode the bus from potassium to hydrogen. I had to tell you that water was an excess. In this question, I told you water was an excess, meaning that it was basically infinite and would never run out. But in the real world, things do run out eventually, all right? And so when we're mixing, just think about like if you're in the kitchen and you're making a sandwich and you have this many pieces of bread and this many slices of cheese, there's a theoretical maximum number of sandwiches that you can make. You're going to run out of one ingredient first. So our job here is to figure out which one runs out first. And that is our limiting reactant. Limiting reactants dictate the theoretical maximum amount of product that you can make. So I'll make some analogies here to bread and cheese, but it does get more complex when we're actually looking at chemical reactions, all right? So let's think about it. If we were in the kitchen doing this chemical reaction, 1 cheese plus 2 breads is 1 sad sandwich. If I told you you have 18 slices of cheese and 30 slices of bread, what is the what's the first question? How many sandwiches can you make? Can you just look at that and like figure it out? How many sandwiches? 15. And you did that all in your head, yeah. But think about the steps you took to get there, all right? So here's another question. Which ingredient runs out first? What made you think it was 15 sandwiches? Which ingredient? Bread. We noticed that, oh, we need 2 slices of bread for every 1 sandwich. I have 30 slices of bread, so that means I can only make 15 sandwiches there. But look at the cheese, all right? We only need 1 cheese for 1 sandwich. So if we have 18 slices of cheese, technically we could make 18 sandwiches, right? But we notice, oh, 15 is smaller than 18. And so that's what makes it the limiting reactant. And that's exactly what you're going to do, but using stoichiometry instead. You're going to do calculations twice, and you're going to pick the smaller number at the very end, all right? So yeah, reactant that produces the smallest amount is your limiting reactant. So in this case, that is the bread. And then our theoretical yield, 15 sandwiches, that is our theoretical yield. It's how much the limiting reactant makes, all right? Oh, we're actually going to do it, all right? So I know a lot of you just did it in your head and you were able to just kind of imagine what that answer would be with simple math in your head. But I wanted to show another way of presenting limiting reactants and how we can get a fuller picture of what's happening here. Because I could kind of do a follow-up on this question all right, where it's the same question. So 18 slices of cheese, 30 slices of bread, but instead of me asking you what's the maximum number of sandwiches you can make, what if I asked, after this reaction's done, how much of the excess reactant is left? So it's basically the same question, but I'm just changing it a little bit. So the idea is, okay, you start with 18 cheese, 30 bread on your cutting board. After you're done making the sandwiches, what is left over on your cutting board? Can you tell me? Cheese, and how many? 3, yeah, and we all did it in our head, but let's use a table to describe it. So this is called a BCA table. It's a way that we can fully comprehend what's happening in a chemical reaction. We don't have to do a BCA table for every stoichiometry question, but this one's a very good example to show fully what's happening, all right? So a BCA table stands for before, change, and after. Before is what's on your cutting board when you start. So in this case, I have 18 cheese and 30 breads, right? And 0 sandwiches, technically, because I didn't start cooking yet. The change line is dictated, 1, by the limiting reactant, all right, and by the change line. Or sorry, the change line is dictated by the limiting reactant and the coefficients that are in this chemical reaction. So 1, 2, 1, all right? So to look at the change line, I think of it this way. Can you look at these numbers and tell me which substance is gonna run out first? Which reactant's gonna run out first? The bread. Yeah, we already determined the bread is gonna run out first. So that means let's just consume all of that bread, all right? Consume all of it, so at the end we have none left. So let's consume all of that bread. Now to fill in the rest of the change line, it's gonna have the same ratio as your coefficients. So you can think of it this way. If I use up 30 breads, how much cheese do I also have to use up? 15, minus 15. All right, so if I use up 30 breads, how many sandwiches do I make? 15, but be careful of the sign. It's not going to be minus 15, it's going to be plus 15 because I gained 15 sandwiches. If you took AP Chem or whatever and you remember ICE tables, this is different, right? This is different. BCA tables describe chemical reactions that go to completion, but I will say a lot of high school teachers just call everything an ICE table. This is technically a BCA table because a full chemical reaction is happening. We're tracking what happens before, what changes, and what comes afterwards. All right, so B, C, now we just add up all those columns and we see, oh, there are 3 breads left. 3 cheeses left, 2 breads, and 15 sandwiches. So that should be exactly what is on your cutting board after that reaction, all right? And so this way we can fully comprehend and see like a comprehensive picture of what's happening, right? So and a BCA table is really great for showing you if you did something wrong. So here, this is what you did in your head already, but I'm just showing it on paper. So let's pretend, we didn't know that bread ran out first, and I'll show you what the BCA table looks like if we did it wrong. So let's pretend, we use up all of the cheese first. What's that going to look like? If we use up all the cheese, how much breads do we need to use? 36, and then we gain 18 sandwiches. But when you do the subtraction, look at it. We have 0 cheese, but we have what? -6 breads? That can't happen. So if you get this and you get a negative value in your afterline, that means, ooh, you did something wrong. You picked the wrong limiting reactant, all right? So I just wanted to show you if you did do it wrong. All right, let's do another one where maybe a BCA table is more useful because you can't do it in your head. All right, here, you partially conduct a reaction and end up with 13 sandwiches, 4 slices of bread, 7 slices of cheese. How much of each ingredient did you start with? So think about what information's given to you. I'm giving you bread, cheese, sandwich, but those pieces of information should go in which line? Remember what BCA stands for, before, change, after. These numbers should go in which line? The after line, yeah. So we have what, 13 sandwiches, 4 breads, 7 cheeses. So I'm asking you, what did you have to start with, all right? I'm showing you the after picture. We got to kind of back calculate to figure out how much we started with. So there's also another piece of information here that's kind of missing, and that's if, you know, we did this reaction, we actually started with 0 sandwiches. So now you can just, I call this, you Sudoku your BCA table. You figure out what are the missing pieces, because there's a value you can calculate right now. If we started with 0 sandwiches and ended up with 13, it tells us a piece of information in that change line. It tells us that this number right here should be plus 13. And that is enough information to fill out that rest of that table. Because remember, that change line has the exact same ratio as your balanced chemical equation. If you made 13 sandwiches, how many slices of cheese did you consume? 13, but what's the sign in front of there? Minus, and this is minus what? 26, all right? So tell me, how much cheese did you start with? 20, yes, 20, and then how much breads? 30. Could you have done that one in your head? Maybe. Writing it out is useful as well, all right, in that BCA table. So remember, the big takeaway is this change line is dictated by your coefficients and your limiting reactant. So notice it's 1 to 1, and in this change line, it also has a 1 to 1 ratio. All right. Okay, let's do another one with actual reactions or an actual chemical reaction. So here I have another balanced chemical equation. Nitrogen combines with hydrogen to give us ammonia. It's already balanced for you. And I give you a picture. So this picture is depicting what line in our BCA table? The before, yeah. Yeah, so there are your numbers, all right? So if you look really closely, how many nitrogens are there? 2. And then how many hydrogens? 1, 2, 3, 4, 5, 6, 7. 7. So there's a couple ways to do this. You can kind of, you can either use a BCA table to figure out, oh, what's my limiting reactant? Or you can just like do the reaction a couple times, all right? Think about, okay, to do this reaction, I need to consume a nitrogen and 1, 2, 3 hydrogens. So if I consume those, what do I get out? What's my product? If I consume those 3 and then a nitrogen, I get ammonia, but how many? 2 of them. So I gain 2 NH3s. Can I do the reaction again? Is there enough stuff? Are there enough ingredients there for me to do it again? You can just think of this like a sandwich. It's a sandwich with 3 slices of bread and 1 slice of cheese. Yeah, there's my slice of bread. And then 1, 2, 3 more cheeses. All right, and I gain another set of ammonias, right? So when we draw this after picture, we have to describe everything that's there. So yes, we have 4 ammonia molecules total in the after picture, but there's also something left over. What else is left over on my cutting board after this reaction? This lonely hydrogen. So this hydrogen is actually still there, all right? So the after picture here, in order to maintain the elements and atoms being balanced, is we will have 4 ammonia molecules and 1 hydrogen molecule left. All right, so that's one way you can do it, but let me show you using a BCA table will give us the exact same answer, all right? If you look at these numbers and think about how many times can you do the reaction with nitrogen? Twice. How many can you do it here? Also twice. So what I'm going to do is consume all of that nitrogen, so minus 2. Here, I'll zoom out a little bit so you can see that. So then I'm left over with 0 nitrogens, all right? But just like the cheese and sandwich analogy, if I use 2 nitrogens, how much hydrogen do I also consume? 6, so minus 6. So if this is, if I use up 2 nitrogens, how much ammonias do I gain? Plus 4, yes, plus 4. So notice it's a 1, 3 to 2 ratio. So this also has to be a 1 to 3 to 2 ratio. And so if you add up all of those columns, look and see what's left. We have 1 hydrogen and 4 ammonias. And is that exactly what we said prior with using the picture diagram? So again, the BCA table is very powerful to give us a comprehensive view of what's going on. But again, you don't always need to do that, to do a BCA table, and I'll show you an example right here. all right? So we will do a full-fledged chemical reaction, determine the limiting reactant, all right? So this is how these are usually given, is I tell you, okay, let's combine 60 grams of aluminum and 96 grams of oxygen to produce this product. Here's the balanced chemical reaction for you. How much product do I make? Our approach is just like with cheese and sandwiches. We need to figure out which ingredient runs out first. And we can't, unfortunately for this one, we can't do it in our heads. We can't just assume aluminum runs out first because there's less of it. We actually have to calculate it, right? So my strategy here is I'm going to assume all of that aluminum reacts to make product, get a number. But then I'm going to do another stoichiometry setup and assume, oh, what if all of the oxygen reacts? How much product do I make? And I'm going to compare those two numbers, all right? And so by doing this, we're going to do stoichiometry twice and compare those two numbers. So since this is stoichiometry and we're talking about masses, we're going to do molar mass, stoichiometry, molar mass. And I give you the molar masses right here of everything, all right? So I'm going to assume all of this aluminum reacts. So let's start with that. 60 grams of aluminum. I'm going to convert that. So we're going to grams to moles of the thing we want to grams. That's what the molar mass stoichiometry molar mass does. So let's convert the gram amount of aluminum to a mole amount of aluminum. So here's the molar mass of aluminum. This is in grams per mole. So this sample is 90 or 26.98 grams in 1 mole of aluminum. Now that I'm in moles of aluminum, I can use stoichiometry to get that there are 4 moles of aluminum will produce 2 moles of my product, Al2O3. So where am I going to put the 4? On the top or the bottom? On the bottom, yes, because I'm in moles of aluminum. That's what I'm starting with. So 4 moles of aluminum on the bottom, and then 2 moles of my product up top. But I'm not done. Since I'm asking for it in grams, I'm just going to go ahead and convert my product into a gram amount. So I will use the molar mass of aluminum that's given, 101.96. Where will the 101 go, on the top or the bottom? Are you sure? Let's check. So remember, 101 is 101.96 grams per mole. Right now we are in the unit of moles, so that means moles goes on the bottom, 101 goes up top. All right, so this goes 1 mole of my product, Al2O3, weighs 101.96 grams. Right? So we just did molar mass, stoichiometry, molar mass. We did like 8 of them today, I feel. But we're not done. We have to check the other reactant as well. So 60 grams of aluminum reacts, so let's do 96 of the other thing. In this case, it's oxygen reacts. Same deal, molar mass, stoichiometry, molar mass, but we need to use the appropriate substances. Oxygen weighs 32 grams, 1 mole up top of oxygen. Now I'm in moles, so I can get on the bus to go from oxygen to my product. So this equality is 3 moles of oxygen gives us 2 moles of my product, aluminum oxide. So the 3 is going to go on the bottom because I'm in moles of oxygen right now, so moles of O2. And then my product, 2 moles of the other thing, go up top, right? Same molar mass, so 1 mole of my product, Al2O3, weighs 101.96 grams. So notice we did stoichiometry twice, molar mass, stoichiometry, molar mass. Make sure you're using the appropriate coefficients for your stoichiometry and the appropriate molar masses for the substances you're working with. And so I usually set up both of them and then put it into my calculator once. So I only have to pick up my calculator once because I'm that lazy. So this first answer should be 3 sig figs because 3 are given. So this first one's 113 grams of Al2O3. And then the second one is 204 grams of Al2O3. So we have 2 gram amounts, but only one of them is correct. Which one is the correct one? The smaller one. Yes, the smaller one. Remember when we made sandwiches? All of the breads only made 15 sandwiches, and all of the cheeses made 18 sandwiches. We chose the smaller one because the breads ran out first. So what we're seeing here is that after making the 13 grams of aluminum oxide, all of that aluminum is going to run out. So this actually tells us 2 things, that aluminum is our limiting reactant, and then the 113, this is our theoretical yield of our product. What that also means is that oxygen is our excess reactant. You can think of it that way too, that this substance will never run out. It won't run out in the course of this reaction. That there'll always be the excess reactant left over. And then this, you might be asking, what is this 204? What is the meaning of the 204 we calculated? It means nothing. It means nothing in the context of this question because we are never going to completely consume all of that oxygen. So that 204 means absolutely nothing, right? So I got 5 minutes so I can do one more question because I'm just building off the last one, all right? Because we can ask this question in the exam as well, and it's much harder. So let me read it. It's the same reaction. 60 grams of aluminum reacts with 96 grams of oxygen, but notice I'm not asking you what is the theoretical yield. I'm asking, after this reaction is complete, what reactant is left over and how much in grams, all right? So in order to do this question, you need to first determine what is your limiting reactant. But we already figured that out, right? Which one is limiting us? The aluminum. If all of that reacts, okay, we know that aluminum limits us. So we can just think, oh, if all of that aluminum reacts, how much oxygen has to be consumed in order for that to happen? So if we figure out how much oxygen is consumed, then we can just do a simple subtraction to figure out, okay, how much oxygen is left over. But here's the thing, this question is hard because you have to do all of this in order to get started here, to know that, oh, aluminum is limiting us. So here's my strategy. I know that aluminum is our limiting reactant, so I'm going to just start with the amount of aluminum that's there. I'm going to use the molar mass just like before, convert to moles so I can get on the bus to use my stoichiometry. So 96.98 grams is 1 mole of aluminum. Now I can use stoichiometry, 4 to 3. So where is that 3 gonna go? Is it gonna go on the top or the bottom? Top, yes, because 3 goes with oxygen. So 4 moles of aluminum goes on the bottom, 3 moles of oxygen goes up top. So remember in the previous question, we went from like aluminum to the product, but in this case, we are looking for, oh, if all of that aluminum reacts, how much of the other reactant also reacts, right? Okay, now we're in mole amounts of oxygen, and so now we get a molar mass. Use the molar mass to get the gram amount of oxygen. So what is that? 32 grams, right? And so if you do that, you should get that 53.4 grams of oxygen is consumed. Is that my answer for this question? No, I did not ask you how much oxygen do you make. I asked you how much is left on your cutting board after this chemical reaction. So to get our answer, how are we going to use that 53? Subtract it. So we're going to do 96 grams of oxygen minus 53.4, and that gives you 42 grams left over, right? So this question is absolutely harder. And the reason is because you actually had to do both of those slides at the same time. You had to figure out the limiting reactant first, apply that knowledge to figure out how much oxygen is consumed and left over. One last thing, if we did the subtraction and we got a negative number, is that okay? No, if you get a negative number, then you probably did something wrong. You probably picked the wrong limiting reactant, right? So just try again. All right, so have a good weekend. Remember, we're not done with this chapter, so there will be, the homework set is not due, but it definitely will be next week. We'll start chapter 4 next week.